Hello, I am Alexandros Apostolos Boulogiorgos from University of Piraeus, and together with Aristotle University of Thessaloniki, we prepare the following work: outage analysis of holographic surface-assisted downlink Terahertz NOMA. The presentation is organized in 4 parts: introduction, system model, performance analysis, and results and conclusions. Introduction. As we move towards the 6th generation era, the demands of massive connectivity of bandwidth-hungry application has exponentially increased. In order to counterbalance these requirements, we need to exploit higher frequency bands, and more specifically, our eyes are in the terahertz band, which is yet non-standardized, and you can find more than 50 gigahertz of available and continuous bandwidth. However, this band suffers from high path loss and penetration losses. As a result, the demand of line of sight is a must. To achieve this demand, we use reconfigurable intelligent surfaces to create alternative paths. However, reconfigurable alternative surfaces operate as bandwidth filters around an operation frequency. Therefore, they cannot support high bandwidth channels. On the contrary, a new technology that solves this problem has emerged. This is reconfigurable holographic surfaces, RHS. And to further increase the spectrum utilization, another technique is used that is called non-orthogonal multiple access, NOMA. This will further enhance the spectrum utilization over the available bandwidth in the terahertz band and enable, finally, massive connectivity. Motivated by this, in this work, we study the synergy of 3 promising 6G technologies, namely terahertz, RHS, and NOMA. This is the first time that a work like this is performed, and our contribution here is to derive novel call-laws from expression for the end-user outage probability that enable the extraction of design guidelines and provide both analytical insights and are verified through simulations. Moreover, we compare these results against the corresponding conventional orthogonal multiple access SIMs. The system model. We assumed a quite simple system model where a base station communicates with 2 user equipment through an RHS. The RHS performs beam splitting. In other words, the beam from the access point at the RHS splits in 2 beams, the one that serves user equipment 1 and the one that serves user equipment 2. The transmission signal is a composite signal that has the information intended for both the user 1 and user 2. Here, PBS is the transmission power over the base station, where alpha 1 and alpha 2 are the power allocation coefficient. Note that the sum of alpha 1 plus alpha 2 should be equal to 1. So the received signal would be at the user equipment 1 to be equal to A1 times the transmitted signal plus the noise. And at the second user equipment, it will be A2 times the transmitted signal plus another noise component. A1 and A2 are the end-to-end channel between the base station, RHS, and user equipment 1 and 2 respectively. And they are equal to H0 times H1, where H0 is the channel coefficient of the base station RHS channel, while H1 is the channel coefficient between the RHS and user equipment 1 channel. A2 is equal to H0 times H2, where H2 is the RHS to user equipment 2 channel coefficient. We assume that the envelopes of H0, H1, and H2 are Nakagami M distributed random variables. And also, we assume that the envelope of H1 is lower than the envelope of H2. As a result, also alpha A1 is lower than the envelope of A2. First, we characterized the order distributed H1 and H2 random variable, as well as we provide the characterization of H0 in form of CDFs and PDF. Let's now go to the second step, performance analysis. Our first step towards analyzing the performance of the system was to extract the SNR at the user equipment 2 when decoding the transmitted signal, when decoding the transmitted message intended for the first and the second user. Here you can see the transmission SNR. Then we also derived the SNR at user 1 when it is trying to transmit its own signal. Based on these expressions, we find a closed form expression for the outage probability of the first and second user that you can see here. What is important to see here is that we need to be very careful with the power allocation factor. If this inequality is not satisfied, then the outage probability will become equal to 1. In other words, the corresponding user will not be able to serve, or to be more specific, both users would not be able to be served. Our results. Here you can see the outage probability as a function of the SNR for different values of the shape parameters of the H0, H1, and H2 channel, and for both NOMA and OMA for both users. What we can see is, first of all, that for a given set of M0, M1, and M2, and for a given access SIM, as the transmission SNR increases, the outage probability naturally decreases. Moreover, we can see that for a given set of M0, M1, and M2, and a given transmission SNR, NOMA always outperform OMA in terms of outage probability. Finally, you can see that for a given SIM and SNR threshold, as the quality of the channels improves, the outage probability decreases. Next, you can see here the outage probability as a function of A1 as for both users and for different sets of M0, M1, and M2. What you can see is there is an optimum M1 that minimizes the outage probability. For alpha, for A1 that is lower than this optimal coefficient, the outage probability decreases. However, for values that is higher than the optimum value, the outage probability increases. Thank you very much.